Kirchhoff was a pretty busy guy, and he also figured out this rule, that the sum of the voltages around any loop is 0. So let's draw a picture so that I can explain this one to you. So suppose I have a circuit diagram like this, and I have maybe 2 resistors and a voltage source connected in a simple loop like this. So this type of connection here, this is a loop because it's a kind of fully closed circuit. So this is a loop. And KVL says that I can go around and define voltages in this loop and that they will add up to 0. So in order to do that, I'm going to need to label voltages on my circuit. So we'll call this, let's say, VS for voltage source. And I will need to write some voltages for my resistive elements. So I'm going to just call them V1 and V2. So now Kirchhoff's voltage law, KVL, around this loop would be used as follows. So I choose some place to start. I'm going to choose the node at the bottom here. Now that's an arbitrary choice. I could have started anywhere. And I'll also choose a direction. I'm going to go clockwise. Again, that's an arbitrary choice. But starting from here, I kind of run around my circuit and I look at what I see. And the first thing I see is the voltage source VS, but I'm approaching from the negative side. So I write negative VS. And then I keep going around my loop and I get to here. And I see V1, but I'm approaching from the positive side. So I write plus V1. And then I keep going and I get to here. And again, I see a positive voltage. So I write plus V2. And then, I'm back to where I started. So now I can stop and I write that these voltages add up to 0. So this is Kirchhoff's voltage law. So it says that I can take a loop that's basically a path through my circuit, and I can add up all of those voltages, and they must add to 0. Now, one thing I should point out, the loop doesn't have to be the smallest path you can find. So let's draw a little more complicated circuit. So suppose I have a diagram like this. Now there's 3 ways, there's 3 loops here that I can use. So I can define a loop like this. This one here is a loop. I can also go like this, and this one here is a loop. Or I can go kind of all the way around the outside like that, and that is also a loop in my circuit. So the important note that I need to make here is Kirchhoff's voltage law, KVL, applies to any closed path through the circuit. So a closed path is one that starts and ends at the same point. So if I start anywhere in my circuit and take whatever complicated path that I like, as long as I get back to where I started, then I can use Kirchhoff's voltage law to analyze that circuit and to write down the equations that would apply to those voltages. So that's Kirchhoff's voltage law. Let's do an example. So in this case here, I have a circuit which has got 3 voltage sources and 2 resistors, and I'm asked to find an unknown voltage V1, which is labeled in orange on that circuit diagram. So the first thing that I'm going to need to do is define a variable, a voltage variable for the other resistor. So I can just draw something in, and I'm going to pick V2 as kind of the next variable name that is not used. Now I can write Kirchhoff's voltage law. So I'll choose the starting point. Again, arbitrary choice, but I will choose the bottom node here, and I'm going to head in a clockwise direction around this loop. So writing Kirchhoff's voltage law here, I approach the 10 volt source from the negative side. So I would write negative 10. I approach my voltage V1 from the positive side. This is continuing around the loop. Approach from the positive side, so I write plus V1. Next, the 12 volt source from the negative side, so that's minus 12. Then V2 is positive, and then I have minus 12 because I continue around my loop and I approach that 12 volt source from the negative side. And then I'm back to where I started. So I am finished with writing KVL, so I say equals 0. So now I can simplify this a little bit. So in particular, I have that my voltages, my numbers here can actually be combined together. So I will get negative 34 plus V1 plus V2 equals 0. Then I would like to calculate what is the actual voltage V1. So in order to do that, I need a little bit more information. And the extra information will come from Ohm's law. So I'm going to specify a new circuit variable, which I'm going to call I for current, and that will be the current flowing in this loop. So the current in a loop like this is the same everywhere in the loop. So Kirchhoff's current law tells me that. I could write, in equals out for every single node, and they would all tell me that the current everywhere in that loop is the same. So there is some current flowing here. And if I would like to calculate these voltages, then I would need to use Ohm's law. So let's use Ohm's law at the first resistor. I'll give it a name. I will call it R1. So Ohm's law at R1. Ohm's law at R1. And I have my current enters the positive terminal, so I write V equals IR with a positive sign. The voltage is V1, the current is I, and the resistance is 5. I can also do Ohm's law at R2. So V equals, let's check the sign, current enters the positive side, so IR. The voltage is V2, the current is I, and again the resistance is 5. So now I can substitute these equations. So I have here equation number 1, equation number 2, and equation number 3. So I can substitute 2 and 3 into equation number 1, and I will get negative 34 plus, so V1 is equal to 5 times I, and V2 is also equal to 5 times I. So then that gives me now an equation which has just one unknown. So I can solve this more simply. So that would be 10I equals 0. 10I will be 34. I is 34 divided by 10 equals 3.4 amps. But the problem asks me, what is the voltage V1? So now I need to go back and look at Ohm's law, and I know here from my second equation that I have a simple relationship for V1. So I have now V1 is equal to 5 times I, which is 5 times 3.4 amps. And so in that way I have now solved this circuit. So I have now the voltages and the currents at kind of all parts of this circuit that I have been able to calculate. So here we used a combination of Kirchhoff's voltage law and also Ohm's law to do this analysis.